Hi class. So in the last lesson, we discussed a particle equilibrium in 2D, and today we will discuss the case in 3D. So as you may already notice, for today, we will get started by talking about the particle equilibrium in 3D, which has x, y, z, 3 axes. So you will be given, so for example here, you are given the 4 forces and its geometry is shown in this figure. So you have the force A, B, C, D, and you know the geometry of each of the cable, and you also know the angle. So you need to find what's the tension. So develop in the cable AB, AC, and AD. So what should we do? So the first, as always, we need to draw the free body diagram of the particle A, and then you need to write down the cable force TB, TC, and TD in the Cartesian vector form, and then apply the 3 equilibrium equations to solve for the tension in cables. So here is a free body diagram. So let's take a look at tension TB. So the TB's direction is exactly the positive direction of the x. So which means the TB will be the size of the TB times by 1i plus 0g plus 0k. Okay, because the tension TB's direction is exactly the direction of the positive x-axis. So what about the TC? Here the vector of TC. So it has a component in XY plane and also a TC in the Z direction. And this angle is already known, it's 60 degrees. So which means our TCZ becomes TC times by sine 60 degree, and TCXY plate become TC times by cosine 60. And then in the XY plate, we have TCXY plate, and also we have TCY and TCX, and this angle is 30. So which means our TCX become TC cosine 60 and then times by sine 30. And the TCY become TC times cosine 60 and times by cosine 30. And the TC become this one. And we put a negative here because the TC's direction, its resolution on the x direction is a negative direction of the y of x. That's why I put a negative here. It will become Okay, here the T6 direction. So what about TD? If we look in from the y-axis into the x and z plate, we can see here is x-axis, and here is our TD direction, and the angle between the x positive direction of x to the TD is 120. So which means our TDX will become TD times cosine 120. And if we look from the y, look into the y-axis, so we can see here the TD, the angle is 60. So the 60 is negative, is the angle between the vector TD to the negative direction of y. That's why we need to put a negative sign, which is negative TD times by cosine 60. As for the TDZ, it becomes TD times cosine 45 degree. Okay, because if we look into the Z direction, here TD and this angle theta is 45. So TD's vector become TD times cosine 120 in the x or in the I vector direction, minus cosine 60 in the G direction, and plus cosine 45 in the K direction. It becomes TD plus times negative 0.5I minus 0.5 G plus 0.707 K. Okay. What else? Okay, what about the vector W? It just become, because its direction is to the negative direction of Z, it will be 300 times 0I, 300 times 0I plus 0G minus 1 times K lab. Okay. And then we can use our equilibrium equation, which is the sum of the F in XYZ direction Z all equals to 0. So sum of F becomes TB times 1I times 0G plus 0K and plus TD And then we can write down sum of the fx on the x direction equals to 0, which is 0g times plus tb which is tb minus 0.25 tc minus 0.5 td plus 0 equals to 0. And for the z direction, for the y direction, also sum of all the forces on the y direction equals to 0, which is 0 times tb plus 0.433 times tc minus 0.5 times td plus 0 equals to 0. Sum of left z equals to 0 becomes 0 times tb plus 0.866 tc and plus 0.707 times tb minus 300 equals to 0. And then you can solve these three equations and get the tb, td, and tc. Okay. You can check your answer right now. So here I find the answer using the equation 2 and 3. You can determine tc and td, and then substituting tc and td into equation 1, you can find the tb. So let's look at example 2. So you have the 600 load is supported by the 3 cord with the geometry and showing this figure. And what's the tension of the AB, AC, and AD? So similarly, the plan is the same. So first we need to draw a Fibonacci diagram of the point A and let the unknown force magnitude to be FB, C, and D. And then you can represent each force in its Cartesian vector form, and then apply the equilibrium equation to solve for the three unknowns. So here the Fibonacci diagram. So you will have point A, we have 4 forces. So FB will be the F times by sine 30 I plus cosine 30G, and because the vector F is in the plane of X and Y, which means it doesn't have Z direct, its component on Z direction is 0. And for the FC is in exactly the negative of the X direction, which will be just negative FC times by I. And for the FD, so FD direction will be the direction vector of the RD divided by the RD's magnitude, so which becomes this vector. So, and then it's time to use our three equilibrium equation. Sum of the forces on the Fx direction equals to 0, sum of Fy equals to 0, sum of all the forces on Z direction equals to 0. And here the equation, and then you can solve the three forces, Fc, Ft, and Fb. And here's the answer. Okay. So let's do a quick check. For example, the particle P is in equilibrium with 5 forces acting on its 3D space. How many scalar equation of equilibrium can be written for point P? So answer should be 3. So because for any 3D problem, we can only write 3 equilibrium equation. Okay. Another question in the 3D, when a particle is in equilibrium, which are the following equation apply? So the answer should be D. All A, B, C should be correct answer. Another quiz is in 3D, when you know the direction of the force but you don't know its magnitude, how many unknown corresponding to that force remain? So because you already know its direction, the magnitude is just a number, so in this case, you only have one unknown. So what about if the particle has 3D forces acting on its in static equilibrium, and the components of the resultant force will be, so because this particle is in a static equilibrium, it means it has to be 0. Okay, the answer should be B. Okay, well, that's pretty much for today's lesson.